It's my pleasure to present to you Professor Aron from Kent State University, and he will speak about common properties of Lipschitz and H infinity functions. Please, Professor Aron.
Thank you. I'm very happy to have been invited, and I hope this is going to be interesting to many of you. Good morning, good afternoon, good evening. This is, as you can see from the slide, a preliminary report, excuse me, based on work with Jose Bonet, Veronica Dimont, Luis Carlos Garcia Lirola, and Manuel Maestre. I am from the US. Bonet, Garcia Lirola, and Maestre are from Spain, and Dimont is from Argentina. So it's somehow a three-continent collaboration, or two collaborations, actually. Okay, so the plan of the talk is it'll be very basic for almost all of it. I hope not too boring, but we'll see. We'll begin with just basic definitions and basic background for the Lipschitz and H-infinity functions, then norm attainment, and then at the end, we'll talk a little bit. I hope to get to talking about a combination of Lip and H-infinity functions. So let's begin with the basic definitions. So M is going to be a metric space, and I already see the first misprint. It's M, and D is uppercase, and then it becomes lowercase below. So anyway, D is the metric, and M is the metric space. One fixes an arbitrary point x0 in M, Y is another Banach space, is a Banach space, and Lip x0, M, Y are the functions from M to Y, such that f of x0 is 0, so at that fixed point, f takes them to 0, and such that for some constant bigger than or equal to 0, one has this inequality at the bottom. And the reason you could wonder about why should we have a fixed point and why should that fixed point value always be 0 is if we didn't have that, then we could have a constant function, and the constant function would not necessarily be 0, but the left-hand side of that inequality would always be 0. So to avoid that, we're just saying let that function at that particular point be 0. Okay, it's a Banach space, this Lip x0 my. It's a Banach space with the norm, which I'm going to be denoting L of f, and it's the inf over all C such that the above inequality holds. Another way of looking at it is if you divide the norm fx minus f of y by the distance from x to y, you want that always to be less than or equal to C. So C is going to be the sup over all such x different from y. Okay, how about H infinity? Well, H infinity is going to be the following. We take two complex Banach spaces x and y. Bx is going to be the open ball of x, and H infinity bxy are the functions from bx values in y, such that f is holomorphic and bounded. Well, bounded is clear what I mean. What do I mean by holomorphic? And essentially what I mean, or not, there are more, I always tell people, more or less any definition that is in any way reasonable that you can think of is likely to be right. One possible definition is you take a complex line through which intersects the ball, so then you restrict the function to that complex line, so it's a function of one variable with values in y, and that's going to be a holomorphic complex analytic function. And it's a Banach space with a natural supremum norm, H infinity. So, okay. And when y are the scalars, we'll just drop the y altogether. So it'll be Lip mx0 and H infinity bx. Okay, now there are three basic results which we're going to need. One thing let me just point out or remind you neither H infinity nor the Lip functions are, except in very trivial cases, are, well, they're Banach spaces, but they're not separable Banach spaces. Okay, a Banach space is reflexive. This is a result of James, which somehow, let's say 1964, and it's reflexive if and only if every continuous linear form attains its norm. The Bishop-Phelps theorem, more or less the same time, is that for any Banach space, the set of norm-attaining continuous linear forms is dense in the dual. And for us, what we're going to be having is this. In our two cases, the Banach spaces Lip and H infinity are not reflexive. So there are going to be continuous linear forms which don't attain their norm. That's by James. On the other hand, by Bishop and Phelps, there have to be lots of continuous functions which do attain their norm, the dense set. So, okay, these are both well-known classical results. Here's one which I think maybe is not quite as well known. It's a few years after them, and it's by a mathematician called Eng. And I think the paper by Eng says something like on a result of Dix-Millet. And the result of Dix-Millet is from 1948. And when it takes a Banach space Z, you look at a locally convex topology tau on the closed ball, such that the closed ball is compact for the tau topology. Then it turns out that Z is a dual space, that there's a vector Banach space V whose dual is isometrically isomorphic to Z. Okay, now one can think for a moment, let's stop for a moment and just think about H infinity. And let's take the easiest case, H infinity of the disk. So, and that has the sup norm. So the first impression is that that's not a very interesting question, because what are the functions in H infinity of the disk which attain their norm, attain the sup norm? Well, you have the maximum modulus principle, which tells you that if a function attains its maximum at a point of the interior of the disk, then it's a constant. So we're going to be looking for something a little bit more interesting than that. That's all I can say for now. So let's consider two applications of the result. So the first involves Lip functions. And what we'll do is we'll consider delta m's, where delta m's are just point evaluations at points of m. And it's clear that each such point evaluation is an element of the dual of the Lipschitz functions. It's an element of Z star. And it's in fact a proper subset of, accepting trivialities of the dual. And what happens is, if you check, then the closed ball endowed with the topology generated by these delta m's is compact. And therefore, what you have is that lip Z x0 x of m is a dual space. And the Banach space generated by these delta m's is a pre-dual. And what happens is this space generated by the delta m's has, in recent history, has been given, a lot of people have worked on it, and they've given three different names to it independently. It's called sometimes transport space. It's called sometimes Aron's eel space. And Godfrey and Carlton call it free Lipschitz space, and that's the name we'll use. But anyway, you see the same idea appearing with different names. How about for H infinity? So let's let Z be H infinity, and you can see it's the same idea. You let now delta X be the collection, delta X be all point evaluations at points of X. So that's an element of the dual of H infinity. And the Banach space generated by these delta X's is denoted, well, script G BX. This, I don't know if it has a name particularly. But so we have these two very similar situations. The two spaces, lip and H infinity, are really quite different, but we end up with very similar situations. So here is the background for the situations. Let's let Y be a Banach space. Let's let F be Lipschitz from M into Y. That there's a unique linear continuous mapping T sub F from Fx0, that's the free Lipschitz space, into Y, such that the diagram commutes. And I'll give you the diagram. It's well, hey, I'll just give me a moment and I'll give you the diagram. Another way of looking at it is, let's let F be a bounded holomorphic function. So F maps Bx into Y, so it's an H infinity function. Then there's a unique continuous linear mapping T sub F from G sub X into Y, such that the following diagram holds. So the top is for Lipschitz functions, and delta, the vertical map, takes M, a point of M, into delta of M, into the free Lipschitz space. And T sub F is the linear, unique linear mapping that you get. And in the bottom, when F is a bounded holomorphic, an H infinity function, you have the same thing. Now, just a moment. What's important, well, several things should be noted. One is that the function F is not linear, so it's not so wonderful. It's not a bad function, but it's not as wonderful as a linear one. And the space M, or the space Bx, is pretty good. It's pretty clear. And what one does is sort of a trade-off, that you trade F, a function which is not linear, for T sub F, which is a linear form, linear functional. So that's very nice. But the price you pay is that you get these very complicated, hard, sometimes not so easy to understand, free Lipschitz space for this G of Bx. And the norm of F as a Lipschitz function or as an H infinity functions equals the norm of the linear operator T sub F. So again, what I'm saying is here, let's see if I can do it. So the norm of F and the norm of T sub F is a linear form, or the norm of F here is an H infinity function, and the norm of TF are the same. Moreover, if instead of Y here, I put C, so now F is a scalar valued, or both F's are scalar valued Lipschitz or H infinity functions, but the T sub F are now linear forms. And in other words, we can see that Lip and H infinity are dual spaces, because TF and F are the same, and TF is in this case, the bottom case, it's an element of the dual of G. Here it's an element of the dual of the free Lipschitz space. Okay, now as I mentioned, neither the Lipschitz functions nor the H infinity functions are is dense. Is neither of them, sorry, is separate, is reflexive, and therefore there are functionals which don't attain the norm. But on the other hand, by Bishop-Phillips, there are plenty of functions which do attain the norm, a dense set. What exactly are these Lipschitz, are these dense subsets? So what I'm going to do is I'm going to spend a little bit of time now talking about giving an answer in one or two special cases. So let's go. Okay, so let's take a look at Lip, and it's a very special situation. So it's where the metric space is going to be the closed interval 0, 1, and the fixed point x0 is just going to be the origin. So these are the Lipschitz functions on 0, 1, scalar valued, such that f of 0 is 0. And now, if you remember, the definition of the norm of the Lipschitz functions is this here. And, well, sorry, is not here. It's this with a soup over x different from y in the interval 0, 1. It's the soup. But a good guess as to what a function being norm attaining would be is that L of f is attained. In other words, the guess would be that the Lipschitz functions which attain the norm are precisely those for which there's an x and a y different, just that L of f is exactly f of x minus f of y, not the soup. And in fact, this guess is incorrect. And the example that I'm going to give, which is due to Vladimir Kadic, Solovyova, and Miguel Martin from 2016, and it requires one well-known fact, which is from Rademacher about Lipschitz functions. And the fact is, and I mean, as you see, the fact is, the guess is incorrect, and I'll show you now why, but it requires a fact, and the fact that it requires is that if f is a Lipschitz function on an interval in R, then the derivative of f exists almost everywhere. And in fact, the derivative of f is an L infinity function. And moreover, the Lipschitz norm of f is the soup norm, the L infinity norm, rather, of f prime. So let's see. Here's the example. So we begin with a Cantor set, C, having positive measure. So it's a little bit thicker than the traditional Cantor set. And let's let f be an interval, be a mapping from 0, 1 into R. F of x is the integral from 0 to x of the characteristic function of C. So let's see. F of 0 is the integral from 0 to 0. So in fact, f belongs to lib 0. It's a Lipschitz function. It's an increasing continuous function. And I should have said, actually, I mean, the argument about why f is differentiable, it follows from the fact that f is, what is it called? Absolutely continuous. So, okay, any case, f is a Lipschitz function in 0 at 0. And the Lipschitz norm of f, which, as I said, is the soup of f prime, is the L infinity norm of f prime. Well, but f prime is just characteristic function of C. And the characteristic function of C in the L infinity norm is just 1, because, I mean, here the Cantor set is positive measure. So it has value 1 on a set of non-trivial measure. Okay. And let's suppose that, I mean, the assertion is that this function this function cannot be approximated by a function which attains its norm. So let's see what happens. So let's suppose that I can find a G here in the Lipschitz functions on 0, 1, such that the Lipschitz norm of f minus G is small. Sorry. So the Lipschitz norm of f minus G is pretty small. Well, we already know that the Lipschitz norm of f is 1, so the Lipschitz norm of G is bigger than 2/3. And suppose further that that G is a function such that its Lipschitz norm is attained. And now let's see if I can. So let me try to draw a picture of what's going on. Okay, here is 1, here is 0, here is x, here is y in the interval, here is g of x, here is g of y. And what do we know? What we know is that g of y minus g of x over y minus x, in other words, it's the slope of the line. This, well, I mean, in this case, there's no absolute value. It should be absolute value in general, is L of G. In other words, the Lipschitz norm of G is attained at exactly this point, X and Y. Okay, let's think for a moment. Let's take two other points, X prime and Y prime, between X and Y. And I claim that G, okay, so this height is G of X, this height is G of Y, and I claim that G of X prime is there and G of Y prime is there. Let's suppose I'm wrong. Let's suppose, for example, that G of X prime is here. Well, so who knows what happened, but in order for the function G to get up to this, starting here, to get to this value, it would have to at some point been increasing beyond the value of the slope. So I mean, similar for G, similar if it's here, how did it get up to there? Well, it would have to have gone above the value. So in other words, what I'm saying is that, let's see if I can avoid erasing everything, but here. G looks like that. And everywhere between X and Y, the value is just on the straight line. Now, recall, we took X prime and Y prime to be in the Cantor set. Sorry, we took C to be the Cantor set. So what that means is, here's an interval. So what I can do is, let me do it over here, without loss of generality, X prime, Y prime, intersection C is empty because it's the Cantor set. And now, so let's see where I am. Okay, there's an X and Y in 0, 1. L of G is here, we just said that. L of G is attained there, so for every X, Y prime and Y prime, L of G is also equal to this. We choose X prime, Y prime such that this occurs. Well, think for a moment about what F is. F is the integral of F of X prime is the integral from 0 to X prime of this, and F of Y prime is the same thing, but the characteristic function is 0 between X prime and Y prime. That's what, because of this. So what I'm saying is that F of X prime and F of Y prime are equal. And here comes the contradiction. Well, we just said that the Lipschitz distance between F and G is at most a third. L of F minus G is a sup over all possible X prime and Y prime at all of G minus F of X prime minus G minus F of Y prime over X prime minus Y prime. But F of X prime and F of Y prime are equal. So that's gone and that's gone. So what I'm left with is G of X prime minus G of Y prime over X prime minus Y prime. But G of X prime minus G of Y prime over X, that's the same as the Lipschitz norm of G, which we had already agreed to be at least bigger than 2/3. So we have the contradiction, and that's the end of the argument. So what it means is that it's, I mean, even in the, what one might regard as the simplest case, where the interval is, the metric space, the general metric space is just an interval 0, 1, and its usual metric, what you might think would be the answer is to what the norm-attaining forms are, norm-attaining Lipschitz functions are, isn't necessarily going to be correct. Excuse me. On the other hand, there are natural situations where the good guess that I referred to, namely, go back, and the guess was that the norm-attaining functionals are exactly those for which the Lipschitz norm is attained. And in fact, there are situations where the good guess would be correct, but they're more complicated, so it's a little bit strange. If M is a compact set and the Banach space, the free Lipschitz space on M, it's X0, it should really be X0 here, has the Radon-Nikodym property, then in fact, in those situations, the norm-attaining elements of the dual space, in other words, the norm-attaining elements of our Lipsch space, are precisely those XY for which we do have equality for the norm. How about H infinity? Well, H infinity is more complicated. Well, I mean, I shouldn't say it's more complicated. It's complicated in its own different way. We've already indicated what the pre-dual of H infinity is. Now, if we take X equals C, so we would have the all points which are just evaluations at points of C, and you take their closed span, and that would be a pre-dual. Another pre-dual is, for X equals C, is the space L1 mod H10. And in fact, in 1978, Ando showed that the pre-dual is unique up to an isometry. So in fact, there's only one. So in fact, this pre-dual and the space generated by this are essentially identical in norm and in every single way. Okay, so now what are the functions which are in H infinity, which are norm-attaining relative to the pre-dual? So in this case, it's relative to the only pre-dual that we know, that we have. And the function is, the theorem is, excuse me, the theorem is that a function f in H infinity is norm-attaining relative to this pre-dual if and only if, and here's what you do. You look at the complex numbers of modulus 1. Excuse me. Now, if f is an H infinity, then it's known that it has radial limits f star almost everywhere on the boundary. So f star of z is going to exist almost everywhere on the boundary. You take its absolute value, and that should be the L infinity or the L infinity norm of f. And you want this set to be a set of positive measure. And if that occurs, then the function f has attained its norm, and it's an if and only if situation. And here, as I said, to talk about f star, it's just that the radial limit exists almost everywhere on the unit circle. Well, let me give you an idea of the proof in both directions. One is going to be a little bit more hand waving than the other, but in any case, I'll give you an idea. Okay, so let's see. Without loss, f, the sup norm is 1, f is norm 1. And let's let K be the set of points of modulus 1 on the circle, such that f star of z has modulus 1, and it has, suppose it has positive measure. And my slide preparation is not wonderful. Define G. So I mean, what happens is this: G is going to be defined to be 0 if Z is not in K, and G is Z is going to be defined to be F star conjugate, complex conjugate divided by the measure of K, if Z is in K. So notice that the measure of K is positive, so I'm not dividing by 0. Well, then you integrate this function, and the integral of this function is going to be 1. The L1 norm of this function is going to be 1. And let's take an h, an arbitrary h, and h1, 0. And let's integrate. So the integral, and the integral is g plus h f star on the circle. Well, that's gf star plus hf plus hf star. But h is an h1, 0. So this disappears. So this is integral of gf star, and you look what gf star is, and you get that it's 1. So in other words, what I've shown is that this acting on f has is norm attaining. And I say we've used the Cauchy integral formula, and the fact that h of 0 is 0. Okay, the other direction, as I say, I'm going to be waving my hands a bit, but can't be helped too much. But anyway, here I go. So suppose that for some G, an equivalence class in L1 mod H0 of norm 1, and suppose that we have that f of G. Remember, G is in the pre-dual. This is in the pre-dual, so f of G makes sense. Now, G is an equivalence class, so it looks like G plus H1, 0, where, and for all H and H1, 0, the integral of f star G plus H is the integral of f star G, just as before. And there's an argument to show that, in fact, the norm of G itself, the L1 norm of G, is 1. And let's use that. Okay, so now let's get a contradiction. So the contradiction is going to be the following. Is going to be for the following thing. What are we supposing? Let's go back to the statement of the theorem. So the statement is, if f is norm, the statement that what I'm proving now is, if f is norm attaining, then the measure of this set is positive. We already proved the other direction. But what I'm doing now is I'm proving that this implies this. So let's go for a contradiction. Well, K is the set of Z modulus 1, such that f star of Z modulus is 1. And suppose for the contradiction that the measure is 0. Well, now we're supposing, remember, we started by saying that there's no loss in assuming that the norm of f is 1. So now, if the set of points where f star has modulus 1 is 0, then what it means is that if you look what Kn is the set of all z's of modulus 1, such that f star of z is less than n minus 1 over n. And what it must mean then is that if you look at all possible n's, you'll eventually get essentially the entire circle, except for the set K, which is insignificant because it's of measure 0. So let's look at f star. As I said, let's fix a kn, which has defined in this way. Okay, so now, as I said, I'll just repeat it, the set of z, the circle, minus k, which is where the function, the radial limit is 1 in modulus, is the union of all of these kn's. And the argument is going to be that what we'll do is we'll show that the measure, so the aim is to show that the measure of kn is 0 for all n. So here I go. I'm sorry about my handwriting. I'm not very good with this pencil. So please don't think that I had something other than coffee to drink this morning. That's not the problem. Anyway, here I go. Well, what we know is that the norm of g is 1. So the norm of g is the integral of g over the entire circle. So it's the integral of g of the entire circle. So it's the integral of g over everything except this set kn plus what's in the integral of g over kn. But now we're supposing that f star g is 1. So the integral 1 is the integral of f star g, but that's less than or equal to the integral of just, see here it's without absolute values. Here I'm just putting in absolute values and dividing the integral into without kn and with kn. Now f star, as we say, is at most 1. So here, if I just remove this, I'm going to have less than or equal to absolute value of g, because f star is no bigger than 1. And on kn, f star is at most n minus 1 over n. So if I replace f star here by n minus 1 over n integral, I have this integral here. And now if one looks, let's see, let's compare, let's compare this and this, and they're the same. So remove them, and what you have is this integral is less than or equal to this integral. In other words, the integral over kn is less than or equal to something less than the integral over kn. So the only way that can be is if the integral over kn of g is, and the absolute value of g is 0. In other words, g in modulus is 0 everywhere on, I mean, this n was arbitrary, so g is 0 everywhere because this happens on all of kn. But we already know that the measure of g on kn is 0, and g is 0 here. So that means g is 0 everywhere. So that means the integral of g, almost everywhere, that means the integral of g is itself 0. And that's a contradiction to g having had norm 1. Okay, as I say, I mean, there's work to be done to show this, and I'm not doing it. Okay, now that is the best possible case. And even for, you know, the way I stated it, X was a complex Banach space with open unit ball B sub X, and we're looking at holomorphic functions on B sub X. But how about when X is Cn? So if X is Cn, and at least 2, then we would have, well, I mean, there are lots of norms on Cn, but let's take, well, I mean, let's take, you know, there are 2, let's say, most natural norms, this Euclidean norm and the soup norm. And it's known that in those cases, H infinity B is the dual of a space of type L10. For instance, if I take Cn with the max norm, so then the ball is just the n disk, so it's the poly disk as the unit sphere. In other words, it's a distinguished boundary, and I'm going to denote it Tn. You can show that f is an h infinity, f in h infinity of dn, if the set of points in the distinguished boundary are such that their radial limits equal the sup of the function, the L infinity norm of the function, as positive measure. If this set has positive measure, then f does attain its norm. Converse, not so clear. So we just don't know. How about when Cn has the Euclidean norm? So it's the same, you can see it's the same hypothesis that f star w, the set of w such that f star w, and Sn is the unit sphere of the ball.
I'm
Suppose
sure
the set of measure. Excuse me?
they are finishing. I will see next time. Okay. Yeah, it's okay. I'll look for that paper. Yeah.
Okay, should I continue?
Sorry, yes, please continue.
Yeah, no problem, no problem. Okay, well then, f attains its norm as an element of L1 mod a, an element of the dual of L1 mod H1, and the converse is true as well. If there is a phi in L1 of Sn norm 1 such that this is the norm, then the set such that f star w is the norm as positive measure. So in this case, we do have. Now, the last few minutes, I want to talk about what we've been doing with Veronica Dimont and Manolo Maestre and Luis Carlos Garcia Lirola. So the idea is we're going to be combining Lipschitz functions and H infinity functions. So let's see what that means. So our Lipschitz functions will always be defined, well, M metric space is going to be the ball, the open unit ball of a Banach space X. And the distance, the metric is going to be H infinity, is going to be the norm, sorry, the metric is going to be the norm of the Banach space. X0, remember, was an arbitrary point of M, and we'll just take 0 to be the ball. So in other words, we'll be dealing with lip bxy at 0. So in other words, every function here is going to take 0 to 0. And here is our definition of the combination. So the notation is not wonderful, but what can you do? HL0 bxy, so it's the Lipschitz functions from the ball to y intersection the H infinity functions on the ball of y. And what we do is we put on it the Lipschitz norm, and you'll see in a moment why that's a fine norm. So, okay, now I should say that, as we'll see in a moment, people have studied things like this in other situations. One example is work of, many years ago by Bruna and Tugores, and people, and their predecessors, which is correct, and people after them as well, who, among other things, studied what's called A1 of D, and A1 of D are the disk algebra functions, whose derivative is also in the disk algebra. So, and here's the definition of the disk algebra. So, I should point out, an important, not so difficult fact is that if f, so let me just write it here, f in H infinity of the disk does not imply that the derivative is an H infinity of the disk. And I'll come back to that one. Okay, so here's the, well, I mean, here's a theorem that is somehow is the beginning, let's say, of the study. X and Y complex Banach spaces. The space I just introduced, so let me just go back to it. So it's the Lipschitz functions intersection the H infinity functions with the Lipschitz norm. So it's a Banach space. And take a look at what I'm saying here. These set of functions, so they're the H infinity functions, which are also in Lipschitz. So they're the same as the H infinity functions, which are 0 at 0. That's for the Lipschitz class, and such that the derivative takes the ball into the bounded operators from X to Y. Let me do it this way. Let me just write this for a moment. F maps, let me simplify making it X to Y, not BX. So then what we have is DF is a mapping from X into the linear operators from X to Y. Now, I mean, it should be BX and B here. So DF is in fact, a holomorphic mapping from the ball of X into this space of bounded linear operators. Okay, here's an explanation of why LF was a fine norm. It's the same as the norm of DF. Now, DF has, well, I mean, DF has a norm being the sup of DF of X. DF is the sup over X of DF of X. No, DF of X is a bounded operator. So that has a norm. And I'm saying they're the same. And when Y is C, so when Y is C, in other words, this is gone, and this is gone, and this is gone. So I have is a function in HL sub 0 of Bx goes to df, the derivative, differential from Bx into, well, if X and Y are both, let's leave it like this. It's an isometry into, and it's an onto isometry if and only if X is C. And I have just a few minutes now. What I'd like to do is give you a very brief argument. It'll have to be brief, of why B holds. So B, let me erase all of this. B is this. So it's just this equality of sets. So, okay, so here it is again. So here I go. So suppose F is in the left-hand side. F is a holomorphic function, which is also a Lipschitz function. Well, then its derivative is a holomorphic function. There's no infinity here. It's just a holomorphic function from Bx into the bounded operators. Let's look at df of x at y. Well, then by definition of the differential, it's the limit as h goes to 0 of f of x plus hy minus f of x divided by the norm of hy. H is a scalar. And if you look what this is less than or equal to L of f. Why? Because we just said, I mean, this is the definition of L of f. The sup of all of these is a definition of L of f. So it's less than or equal, any one of them is less than L of f. So what I'm saying is this holds. So in other words, df is, and if you take a look, it's independent of y, it's independent of x. So it's a bounded holomorphic mapping, just as I want. And to conclude, Let's go the other way. Suppose that f is an h infinity function. Value is in y, f of 0 is 0. And suppose that df is an h infinity function. So we're supposing this here. I want to show, well, what do I want to show? I want to show that f is in here. So it has to be an h infinity function, which already is given. I have to show that it's a Lipschitz function. Well, let's see. The mean value theorem applied to any x and y in B of x gives us that f of x minus f of y. This is just a multivariate version of the mean value theorem, is less than the norm of df times the norm of x minus y, which in other words means that f of x minus f of y is Lipschitz with Lipschitz constant at most the norm of df. What have I proved? Well, if it's in here, then as I say, we already know that it's automatically h infinity, and this shows here that it's a Lipschitz function. And I think that's, well, I think I'm out of time, and in any case, well, I guess there's a little more I can say. Yeah, I mean, it's just the same, that if x and y are both c, then HL0 of d are the h infinity functions, such that the derivative is also an h infinity function. And I thank you for your attention.
Thank you very much for the very interesting talk. And please, if there are questions, yes, Professor Aristides. Just your microphone.
No, I'm sorry, I was confused. I just wanted to clap to show my appreciation for a very nice talk. There was no question. Yes. I'm not used to Meet's machine. I use Zoom. So
actually,
thank you.
Is there a way that I can see you? All I can see is my own screen.
You
can
see
probably
me if you unshare your screen.
If I what? Unshare?
Yes,
if you are unshare, yes.
Well, let's see if I can do that.
Yeah.
Here we are.
Here I am.
So please, if there are questions.
Yeah, maybe I have a couple of questions.
Sure.
Please, Alexey. Yes.
Yeah. Well, in your construction of Lipschitz space, you use, of course, distance by defining f of x minus f of y divided by d of x and y.
Right.
So if there are a possibility to do similar things, if instead of the distance, you will use modulus of continuity.
Oh.
I mean, the answer is I don't know. I mean, other questions are you could ask like Holder inequality, Holder continuous. So you have other inequalities. I mean, I'm sure they have been studied, and you know, let me say this way: I'm pretty sure that they've been studied, but I'm absolutely certain that I don't know.
Yeah, you know, because maybe it's another question. In your last result, you showed us you have the inclusion of one space to another space, in the sense that if function from that space that such estimates are true, but it may be more tricky with modulus of continuity instead of distance. So maybe some kind of intersection of spaces. Maybe one included into another, maybe another included into the other one. So, but it's maybe just a general wondering, maybe not a sharp question, just a general wondering.
Yeah, and I mean, it's a good thing to ask. And I mean, I've never thought of that. And I mean, about my co-authors, I don't know either. But okay. I don't know.
Okay, it's a question to study.
I think I have small questions, Aron.
Yeah, right? Please.
Yeah, I think these two spaces are also having the algebraic structure. So they are Banach algebra. Is it worth considering the Banach algebra structure to bring in?
Yeah, I mean, that's something that, I mean, H infinity in a natural way is a Banach algebra.
Mhm.
Have to do some adjustment. Well, what you're saying, if you're assuming without the range space Y scalar are the scalars, right?
Yeah, in some special cases only I am talking about.
Yeah. So Y, and you have to do some adjustment to make, you can make a Banach algebra situation with some kind of adjustment on the norm of the, your Lipschitz norm. But I don't know if that's been, I mean, we have not studied that. I mean, there's, so I don't know.
If y is equal to c, then I see that the first structure, lip m sub x0, will be a maximal ideal, I think, and then it will be closed. So can we do more having the maximal ideal at hand?
I don't know.
Okay.
I guess I should have begun.
I have a small question. May I ask?
Yeah. Yes.
Quite a good deal is known about the approximation properties, the bounded approximation property of the free spaces associated with a certain space or certain metric space. Do we have similar in H infinity?
Well, I mean, let's see. H infinity, if H infinity, yeah, let me address the question in the following way. If H infinity, sorry, look at the pre-dual of H infinity, just of the disk. So if you look at H infinity of the disk, its pre-dual is what I call script G of the disk, would be script G of the disk. And the question is, does that have the approximation property, say? Now, if it does not have the approximation property, it would be extremely interesting, because if it does not, it would imply that H infinity, the dual, does not. And that's, so, I mean, in some sense, that's a harder question than the unknown question about whether H infinity has the approximation property. So it would be nice, I mean, frankly, it would be nice to know one way or the other. It would be a wonderful result if the pre-dual did not have the approximation property, but I just don't know. For H infinity of the ball of X, where, in other words, I'm replacing the disk now by the ball of an open ball of an arbitrary Banach space. And I'm taking always at the moment the range to be Y to be the complexes. What is known is that L infinity, little L infinity, is contained in it. It's little L infinity somehow is ubiquitous in this. So that's one thing. And the other thing is that if the dual of X, if H infinity, if looking at H infinity of the ball of X, the dual of X star, is a complemented subspace of this H infinity of the ball of X. So what it means is that if you're looking for approximation property, it better be that the dual space of X, of the underlying space, has it. Because, I mean, otherwise you're lost. And as I say, also, I mean, it's in some sense, well, that's some news. And then also, in some sense, it's, well, bad news, because, I mean, containing L infinity, there are lots of wonderful good and wonderfully bad things contained in L infinity. So I mean, I don't know. I think I should have, rather than thanking the audience thanking you for attending and thanking Alexey for inviting me, I think I should have begun my talk by saying, no matter what you ask, my answer will be, I don't know. But in any case.
Okay, thank you.
Maybe I have one more question.
Yep.
Can I?
Fourth.
In first slides, you showed correspondence between a function and an operator TF. So you have a function,
Right.
and you correspond to every function, you correspond to certain operator TF. So can you kind of study this class of operators like Topless operators, like other operators?
No, exactly.
These symbols.
And that, I mean, to my knowledge, and I mean, in many situations, this has been done. And you can look, for example, if TF is, as you say, compact or topless or nuclear, or I mean, many different kinds of operators. And then you can see what kind of related associated functions F in lib or in infinity there are. To my knowledge, it has not been done in the two cases that I described. That's to my knowledge.
No.
So
Okay.
in the infinity cases, I don't know if anything has been done. As I say, I mean, this is preliminary work, so it's not. But anyway, that's.
Yes, too many ideas can be obtained from this. Okay.
Yeah. Yeah.
Thank you.
Thank you. So if there are some more questions,
well,
please.
Thank you all for attending.
Yeah.
I hope it wasn't.
Thank you very much, Professor.
Let's
thank you.
Thank you.
Thank you very much.
Thank you.
Thank you.